Well, hello and welcome back, you rascally little environmental science students. We are going to transition to a new topic, and that new topic is going to be nuclear power. So we're kind of moving ourselves away from fossil fuels for the moment, um, but still the same enduring understanding is that humans use energy from a variety of sources, resulting in positive and negative consequences. The reading you ought to do to accompany this lecture is section 14.5, pages 435 to 444 from that Miller textbook. So we're going to begin with some basic atomic structure. All right, and this is going to be important as we talk about isotopes and radioisotopes and how that eventually leads us to our ability to make electricity from certain properties of certain isotopes. So we'll begin with the basics here. What you see in the little image right here is what's called the cloud model of an atom, right? And so in our best estimation or our best representation, I should say, is a better word, of atoms nowadays is this cloud model. And basically the way that is we have a nucleus, and which is very small compared to the overall space that an atom might occupy once you factor in the orbits of an electron. But that nucleus contains protons and neutrons. All right. Protons have a positive charge, and neutrons have a neutral charge. All right. Now, electrons are the negatively charged particles that comprise atoms, and those essentially orbit, for lack of a better word, around that nucleus. And so that cloud you're seeing in that cloud model is those electrons uh, occupy various orbitals and energy levels, all right, and move really fast. Now, electrons are exceptionally small, even compared to neutrons and protons, right? They don't really provide any sort of mass per se, but they do provide electrical charge. All right, and a neutral atom, or if we say the word atom, we are assuming it's neutral. Otherwise, we would call it an ion, which is another topic that's not so important right now. But um, it has the same number of protons as it has electrons, resulting in essentially a neutral charge. All right. Now, atoms and radioactivity, and this is leading us a little bit closer to our nuclear power thing here, but um, we have to understand the concept of isotopes first. So first of all, the mass of an atom, which by the way is exceptionally small, and we use units called atomic mass units. Um, so that mass is essentially the sum of the protons and neutrons. So basically, we're talking about the mass of that nucleus. Again, those electrons, they are an important part of atoms in terms of their behavior and reactivity, right? But they don't really contribute to the mass of an atom. So the atomic number is the number of protons only. All right, so each element essentially has its own atomic number. So we could start with a very simple one like carbon, right? So carbon has an atomic number of 6. Okay. Now, so if you looked at the periodic table, for example, you would see that carbon is element number 6 on the periodic table. That's because it has 6 protons. All right. Now, when we talk about the term isotopes, we're talking about the same element, right? So we can maybe have different varieties of carbon, right? All of them have 6 protons, all right, or the atomic number 6, and that's what makes it carbon in the first place. Now, what can happen in the nucleus of a certain type of element or certain type of atom is the number of neutrons can vary to within a certain kind of small range of numbers, right? So, for example, with carbon, we actually have 3 varieties or 3 primary isotopes. We have carbon 12, we have carbon 13, and we have carbon 14. All right. Now, this is the mass number, all right, which is the sum of the protons and neutrons in an atom. So in the case of carbon 12 here, right, we would have 6 protons and 6 neutrons. 6 plus 6 makes 12, right? In the case of carbon 13, we would have 6 protons, 7 neutrons. 6 plus 7 makes 13. And in the case of carbon-14, we would have 6 protons and 8 neutrons. But notice the number of protons is constant. That is what makes carbon carbon. If it was 7 protons, it would no longer be carbon. It would, in fact, be nitrogen in that case, which is number 7 on our periodic table. All right. So these are the isotopes of carbon. Same type of atom, different mass due to slight changes in the number of neutrons in that nucleus. Okay? Now, um, when we have what's called a radioactive isotope or a radioisotope, that's when we have one that is unstable. So again, we can go back to our 3 varieties of carbon, 6, 6, 6, 12, 13, and 14. All right? And so some isotopes of particular elements have an unstable nucleus. That means that that nucleus is not going to remain intact in the way that it currently is. All right. So, for example, we have carbon-12, which is stable. Carbon-13, also stable. Carbon-14, radioactive. Okay. And so when you have a radioactive isotope, that means that that nucleus is going to change over time to become stable. All right. Um, and so it ejects energetic particles. It might be an alpha particle. So in the case of our very large elements that are radioactive, right, they eject like little pieces of their nucleus called alpha particles. It could be uh, gamma radiation. It could be um, or basically beta particle emission from a nucleus, depending on what type of change needs to happen. All right. But when we say something is radioactive, that means the nucleus of that particular atom is unstable, right? And it will undergo some sort of change, right, in order to become stable over time by emitting some form of radiation or energetic particles or rays. All right. Um, so another example is uranium-235, which is one of our primary fuels for nuclear power, will decay over time to become lead. It will undergo several different types of decay. It's called a decay chain. We won't get into that right now. All right. But another important thing is to understand is with radioactive decay, right, we are emitting energy. All right. And in fact, what's happening is uh, mass, right? We're losing a little bit of mass as it escapes that atom as energy. And we'll talk more about that in just a minute here. Okay. Um, and then each isotope decays based on its own half-life. Half-life is another topic that's important for the College Board, but we're going to address that a little bit more during class because it's a mathematical concept. All right. Now, it is important to understand what we mean when we say half-life. So basically, when you have a radioisotope, you have to remember that atoms are extremely small. And so when you have a measurable amount of a substance, let's say a handful of something, right, we're talking about some ghastly number of atoms. All right. And amongst those atoms, some of them are going to be radioisotopes. All right. So the ones that are radioisotopes decay at different rates, kind of based on a lot of factors, right? But some radioisotopes have exceptionally slow decay, right? So in order for half of the present atoms to decay, it might take somewhere around millions of years, right? In the case of neptunium, other isotopes have exceptionally fast half-lives, which means iodine, for example, 131, only requires 8.1 days for half of the present isotopes to decay to a stable form. Okay, but again, this is something we'll talk about a little bit more in class. So let's get to the nitty gritty of nuclear energy. How do we go from this idea of radioisotopes to electricity? And by the way, when we talk about nuclear energy, we are primarily talking about electricity. All right. So um, we can basically we can release energy in large enough quantities to produce electricity, or in uh, more violent cases like nuclear weapons, right? Through two processes called fission or fusion, which is not the same as our traditional radioactive decay. And we'll talk about what it means here in a minute. But fission, okay, refers to the splitting of big atoms, okay? And fission is the way we currently produce power for electricity. I'm going to use a different color uh, in our nuclear power plants, right? So it's the splitting of an atomic nucleus into two smaller fragments, right? And it's accompanied by the release of a large amount of energy. Okay, fusion would be taking two smaller elements and squishing them, fusing them into a single new element. So, for example, that's what powers the sun, by the way. And all stars is the fusion of hydrogen into helium, and then eventually helium into carbon, etc. All right. In either case, so fission, which is the splitting of a large element, fusion, which is the putting together or fusing of two lightweight elements, either way, we get a large amount of energy. And so our nuclear warheads, for example, we can have fission bombs or we can have fusion bombs or hydrogen bombs. Either way, huge amounts of energy can get released. Now, in the case of electricity production, we're obviously trying to run that reaction at a slow enough rate that we generate heat and energy, but not at such a fast rate that we get large explosions. So in the US, as of 2016 anyways, nuclear power provides nearly 20% of our electricity right now. Again, this is specific to electricity, only one of the forms in which we need energy. This does not account for heating and cooling, does not account for transportation. We're just talking about electricity production at this 20% mark. Okay, so it is not as much as either natural gas or coal is, but it is still a very important uh, component. Almost one-fifth of our electricity production comes from nuclear power. All right, so for nuclear fission, for fission to occur, all right, we need certain isotopes that are referred to as fissile. And so primarily we're going to rely on uranium-235, all right, or plutonium-239. Now, uranium-235 is a naturally occurring isotope, so we can mine uranium. Uh, and again, Australia, I believe, has the largest uranium deposits as of right now that have been discovered. But there's a slight problem in that 99.3% of uranium is uranium-238, not visible. All right, only 0.7% is uranium-235, that particular isotope that we can use for fusion or fission, excuse me. So in this case, right, our uranium has to go through what's called an enrichment process, which is basically you separate out some of the uranium-238, right, leaving uranium-235 until we get to a point that we're at about 3.5 to 4.5% for a fission reactor. So that's what they call uranium enrichment, okay? Which, by the way, is one of the technologies that's kind of kept under lock and key and watched very carefully as to which countries have access to that technology. Because if we can enrich it for a nuclear reactor, theoretically, you can enrich it even farther to build nuclear warheads. All right. Now, we could potentially also use plutonium-239, which is actually synthetically created from uranium-238. And in fact, it's a byproduct of uranium fission. All right. And so, in essence, in using uranium-235, right, at 3.5 to 4.5%, we are actually also simultaneously creating plutonium, um, which could be used for fission as well, or for nuclear warheads. All right. So the way the fission process works is once we've got our uranium fuel pellets, all right, uranium-235 is bombarded with neutrons, all right? The nucleus of uranium-235 absorbs a neutron, which actually causes it to split into smaller elements, right? Now, in that process of splitting an atom, what's happening is some of the mass of uranium-235 basically is released from the atom as pure energy, or heat in this case. All right. Now, when that atom splits, it releases energy, right? Or some of the mass escapes as energy, but it also releases more neutrons, which can bombard even more atoms, split those, which release energy, release mass as energy, which can release even more neutrons, which can split even more atoms. So we get this chain reaction, all right, um, releases heat. All right. Now, once that reaction or the heat from that reaction is built up, all right, um, in come what are called control rods to slow the reaction down to prevent it from running away and getting too hot. So we get a controlled nuclear chain reaction, which is basically bombarding the nucleus of uranium-235 with neutrons. That splits. Some of that mass escapes the element as energy. All right. Then we use that heat to boil water. Water creates steam to spin a turbine. Turbine powers a generator and out to the grid. Right. So very similar uh, to coal and natural gas or fossil fuel electricity production, except in this case, the heat source is not combustion of a carbon fuel, it is the fission of uranium. All right. Now, there's several advantages and disadvantages of nuclear energy. So, for example, because we are not burning a fuel, we are going through fission. So this is not combustion, right? There's essentially no air pollution. All right, so it is not a combustion reaction, so we're not releasing smoke and particles and carbon dioxide. All right, so it's essentially a carbon-free source of electricity. Um, Now, it is worth pointing out that we need to mine uranium, and we use fossil fuels in order to mine it, right? And in the construction of a facility for nuclear power, there's a fairly large carbon footprint associated with the construction and mining, but it's still only 1/6 of the carbon footprint of coal. All right. Now, like fossil fuels, it is an exceptionally reliable source of energy available 24/7. All right. It's likely to last longer than fossil fuels and land use associated with it because we need so much less fuel compared to coal. So, like a pellet of uranium oxide, for example, is equivalent to several tons of coal. We end up with much smaller land use footprint. Now, downsides, it is a non-renewable resource, much like our fossil fuels. We don't have any more uranium than what the Earth has already provided. Does require large amounts of water for cooling, and we end up with what's called thermal pollution. So basically, we use the water for cooling, but that water gets heated up in the process, and if that water escapes into the environment, it's not radioactive, by the way. It never touches radioactive material; it just cools through a heat exchange. But thermally polluted water has less dissolved oxygen in it, which is bad for fish. We'll talk about that in Unit 9 later. Um, we do generate radioactive waste, for which storage is a major issue, another topic we can talk about in class in greater detail. Um, and many of the steps for mining and disposal require fossil fuels, and it's expensive. And there's the whole worry about weapons proliferation. All right. We're going to talk quickly about important nuclear accidents, which are another disadvantage, right? So, first of all, there is the possibility of what's called a nuclear meltdown. So, essentially, the control rods, which are supposed to slow that reaction down to a manageable rate, all right, perhaps something goes wrong with the cooling or with the ability to control this reaction. So, essentially, too much heat is generated, right? That ends up causing a melting of the pellets and the casing and a actual literal meltdown of the reactor core. All right. Now, um, there have been essentially three primary nuclear power plant accidents. And one of the things here is with radioisotopes and radioactive material is it can escape into the environment and it can be extremely dangerous. All right. And it remains dangerous for exceptionally long periods of time. Okay, so we'll talk about three primary accidents. The first is 3 Mile Island. This is the only accident in the U.S. This was March 28th, 1979. So I was just a wee little lad at this time. All right, and so there was a partial meltdown of one reactor, which caused essential shutdown of the plant. Now, in this case, it was a coolant issue, but the containment building inside which, so basically all reactors are inside what are called containment buildings, which are steel and concrete enforced structures, which are designed, as the name implies, to contain radiation in the event of a meltdown. All right. So the containment building did its job in 3 Mile Island in that, yes, there was an accident, and yes, radiation escaped the reactor, but it did not escape that containment building. So there was basically no radiation that escaped into the environment, and no deaths associated with this particular accident. It did, however, have the important impact of increasing public fear of nuclear power. All right. And as many as 51 new plants planned for construction in the US were halted or basically put on such long timelines that they just decided to scrap it altogether. All right. So there's a big public perception that issue with nuclear power that it is unsafe. All right. And events like 3 Mile Island heightened that public perception of lack of safety. Now, the worst nuclear accident in history occurred in Chernobyl, Ukraine on April 26, 1986. This was actually a safety test they performed that failed catastrophically. And so in this case, radiation fully escaped the facility and actually spread over much of Europe, particularly in the Ukraine, Russia, and Belarus. All right. Um, and there were nearly 50 deaths directly attributed to radiation exposure, although the number of cancer, like thyroid cancer, for example, and leukemia cases, are really hard to point directly back to this. But I think it could be in the neighborhood of 100,000 people potentially if we associate many of those cancer cases with this particular accident. This resulted in essentially a permanent evacuation of a 30-kilometer radius for at least 300 years. All right. And then we have the Fukushima Daiichi plant, March 11th, 2011. All right. So this was not a system failure directly due to the mechanics of the plant. This was as a result of an earthquake and the subsequent tsunami, which essentially took out all the backup power and so on at the nuclear power plant. So it wiped out the backup generators, so there's no way uh, to control the nuclear reactions that were occurring. And so there was this basically slow buildup of heat in these reactors. But because they had evacuated due to the tsunami, right? They knew that the plant was running out of control. They were also able to evacuate the surrounding area. So luckily, again, um, there were no direct deaths to this accident. Okay, but historically speaking, and kind of understanding the timeline, is that it had been quite some time since any sort of appreciable, more than 20 years since any sort of appreciable nuclear accident had occurred. All right. And around this time, there was a lot of talk about increasing reliance on nuclear power as a substitute for fossil fuels for 24/7 base load electricity production, particularly in light of our search for carbon free or at least low carbon alternatives to fossil fuels. This put a big question mark back on this. Well, there was a lot of momentum to increase nuclear power globally until March 11th, 2011. All right. So the questions I want you guys to consider is, do the benefits of nuclear power as a low carbon and constant source of energy outweigh the disadvantages? Again, if we're trying to truly combat climate change and find low carbon or no carbon alternatives for electricity production, nuclear power is attractive. All right, because it is not intermittent like solar and wind, in that we can use it at any time of day, any time of year, regardless of weather, climate, etc. So it's a great baseload supplier of electricity. All right, but we have issues with waste, we have issues with safety or safety concerns. So is this going to be a solution for us as we move forward and look for low or no carbon alternatives to fossil fuels? All right. Now, other topics for class discussion, because we still have not done the topic of nuclear power justice. Yes, we're going to talk about waste. How do we store it and why is it such a problem? We'll also talk about innovations in nuclear power, right? New and much safer reactor designs, which reduce waste significantly. And what's the future of fusion power, which gets rid of a lot of the concerns we have with regular fission power. All right, this one got a little long, and I apologize.